We have Griffiths Quantum Mechanics, problem 5.29. Talking about Bose Einstein condensation and all kinds of fun stuff. So the first thing we need to do is show that for bosons, the chemical potential must always be less than the minimum allowed energy. And a big fat hint that he gives us is that this number density, if I'm using the right term, so this cannot be negative. So it's always greater than or equal to 0. All right, so let's just look at this. All right, so if we go and find this equation, we find the, all right, so this is in 5.103, if you're following along in the book. Let me just make sure, know what, yeah, I'm not sure exactly what, I think he calls this the number density. Anyway, for bosons, we have a 1 over e to the epsilon minus mu over kBt, oops, divided by kBt. And then for bosons, it's a minus 1 right here. All right, so this has to always be greater than or equal to 0. All right, the number on top is positive, so the number on the bottom must be positive, which tells us that this exponent e to the epsilon minus mu over kBt, so this bottom has to be positive, right? So this must be greater than 1. All right. So in order for that to happen, this exponent up here has to be positive. All right. kBt is Boltzmann's constant. Boltzmann's constant is positive. Temperature. This is absolute temperature, right? So it's positive as well. And we're left with just this epsilon minus mu, and that has to be greater than 1, or greater than 0 actually, right? So yes, yeah, greater than 0. All right, therefore epsilon must be greater than mu. Okay, so for part B, he gives us the example. Let me flip back to my part B. So he says for the ideal Bose gas, this mu is actually less than 0. All right, for all temperatures. So in this case, we need to show that the chemical potential as a function of temperature increases as T decreases. So this will go up as the temperature goes down. Okay, so and we are assuming that N and V are held constant. And he gives us another big fat hint. Study equation 5.108 with the minus sign. So equation 5.108 is, so here's the number, particles V over 2 pi squared. Integral from 0 to infinity. We have k squared. We have an E. Okay, so I'm just going to use the epsilon instead of the whole momentum over 2m. Right? Over kBt. Okay, and a minus 1 for bosons. Alright, so we're going to study this. Alright, so N is held constant, V is held constant. Right, So basically this integral has to be constant. And we don't have anything, you know, weird going on as like a dependence of k on t, or you know, there's no like weirdness going on. So this integrand has to be constant. Okay. So with k constant, basically this exponent down here, right? Here's where things are changing, but this exponential, this whole thing in the circle has to be constant. So e to the epsilon minus mu divided by kbt is equal to a constant. All right. So what are we looking at here? I'm just going to put this in terms of other constants. All right. So all right, let's write this one more time. So epsilon minus mu, all right, divided by kbt has to be constant. All right. So looking at this, pretty much what we have is, you know, an epsilon over kbt minus mu over kbt equals constant. All right, so probably beating this to death, right? Let's just multiply everything by kbt. All right, I'm just going to write this as some constant a minus mu, all right, is equal to some other constant b multiplied by t. Okay, so since a is constant and b is constant, as all right, as t goes down, right? So this side is decreasing. That means this mu must become larger, right? Because of this minus sign, right? So we're subtracting more off. Basically, this side decreases, so this side has to decrease, so mu has to increase. All right. So that's just what we've shown here. Again, probably ran around that one a lot more than we needed to, but it's late. So, part C, a crisis called Bose condensation occurs when, as we lower the temperature, the chemical potential, mu as a function of T, hits 0. All right, so the chemical potential is negative, right, and it's climbing as T goes down. So it increases as T decreases, what we just showed, and it's negative, so it's climbing towards 0. When it hits 0, that's when this condensation begins. All right, so we're going to evaluate the integral for mu equals 0 and obtain the formula for the critical temperature T sub c at which this happens. So below the critical temperature, the particles crowd into the ground state in a calculated device of replacing the discrete sum. All right, yada, yada, yada. You can read that at the beginning of the video. All right, and he gives us a nice hint real quick. I'll just write this part down. So the integral of from 0 to infinity, x s minus 1. Stay on the paper. E to the x minus 1 dx. Right. We have an Euler gamma function evaluated at s, and then a Riemann zeta function. Well, also evaluate this. Alright, we're going to look up the appropriate numerical values. So here's the integral that we're doing. That same one, b over 2 pi squared, a little infinity here, k squared, e h bar squared, k squared divided by 2m. Alright, and then normally there's this minus mu right here, and then the whole thing is divided by kbt, but again, we're finding the critical temperature at which mu is equal to 0. So we won't write that part. We won't write the mu equal to 0. We'll just put the kBT. We'll just only divide this energy term by it. Okay, and then we have a minus 1 and integration with respect to k. Okay. So if we want to get this into this form, it's pretty obvious what sort of substitution we need to make, right? So here we go. X, this big lump right, this bunch of stuff right here is x. H bar squared, k squared, 2m kBT. Okay. All right. So let's see what we've got now. Dx is equal to h bar squared all right. So let's see what we can plug in here. Okay, well, we know we have an e to the x minus 1 on the bottom. Kind of end up doing this in parts, I think. We still have a k squared up on top. And now we're going to solve for dk here and plug this in. So we have so just looking at this equation, we can kill the 2's. So we have an m kBT divided by h bar squared k, and then we have our dx. Alright, so this k is going to kill one of those k's, and then we'll have to plug in what we get for this. So real quick, let's solve for k right here. 2m kBT over h bar squared. Alright. And then there's an x. This is all to the 1/2, and then an x to the 1/2. Alright. Okay, so now we just have to pull all these constants out, stick the k's up, plug this k in, and we should then be able to plug it into our wacky integral with the gamma function and the zeta function and all that. Alright, so we have a v over 2 pi squared. We have a 2m kBT or h bar squared to the 1/2. Then we have this factor right here, m kBT over h bar squared. Okay, and then we have our integral, which turns out to be x to the 1/2 power over e to the x minus 1 dx. evaluated from 0 to infinity. All right. Let's see. So now we're just going to find out what S is. And maybe we can simplify this down somewhat. So, S, all right, everything matches up just great. We know S minus 1, all right, from this formula right here is equal to this exponent here, which is 1/2. So, therefore, S is equal to 3/2. All right, so here we go. N is equal to, and let's see, what can we do with all this? Probably, that's the one thing about watching these videos, you can fast forward as much as you like. So, let's see, I'm going to put a square root of 2, and then I'm going to have an mkbt. Put this, I'm going to combine these two to get a 3/2 power. Okay, and then we have an h bar. We'll have this gets taken down to just 1 power of h bar, but then we have 2 of them out here, so we end up with 3 altogether. And now we put in our gamma function, 3/2, and I'm trying to remember how to draw zeta. Whoa, okay. Whatever. Squiggly. I look at zeta for a second then I can usually draw it better. Okay. Alright, and of course I neglected to look up the numerical values beforehand, so I'll do that real quick. Alright, so went ahead and looked them up. The zeta function, we get about a 2.6124. For the Euler gamma function, we get a square root of pi over 2, so courtesy of Wolfram alpha. So we can simplify this. I'm just going to bring the 2.6124 out in the front. What can we do here? So this square root of pi will give us what, a 3/2 pi downstairs. And then we'll have this 2 on the bottom. So let's see, I'll have a v. I'm going to have a square root of 2 over 4 now. Bring this h bar cubed. Okay, so then since this pi is to the 3/2 power, I'm just going to bring that in with the mkbt. Make this whole thing here to the 3/2 power. Alright, that takes care of our zeta, that takes care of our gamma, and you know what, I think this is our answer here for part C. Okay, forgot what we were solving for. We were actually supposed to solve for the temperature here. Okay, so let's go ahead and do that. You know what, I guess we can make a couple more changes real quick. For example, here's a 2 squared and a square root of 2. So this 2 can also go into this mess right here. So we have a 2 pi, and let's just bring in an h bar squared as well, like this. Alright, so we're able to gather a few things together a little bit more. All right, let's go ahead and solve for TC. Well, let's see. How should we do this? Well, n over v. 1 over 2.6124. Okay. And then all of this to the 2/3 power, and then multiplied by 2 pi h bar squared over m kb, and this is equal to our critical temperature, right? So this is the temperature at which, so we have this chemical potential which starts negative and rises up to 0, and as the temperature is lowered, right? So when the temperature is lowered down to this critical temperature, T sub C, that is the point at which the chemical potential of this Bose gas will hit 0. So that's the point when the Bose Einstein condensate begins to form. All right. And then for part D, it's just kind of a plug in the numbers and see what you get. And the number for that turns out, I believe, to be around 3.1 Kelvin. So a little bit different from the experimental value of 2.17 Kelvin, but fairly pretty close for a result like this.